Right. Hello, everybody, to our next lesson where we are going to have to remember arithmetic sequences and we'll build one step on top of that. So let's just, many E's, let's just remember the arithmetic sequence by way of an example. I think is fine. I'll stick to that first classic one. 1, 4, 7, 10, 13, and so on. Now we have two kinds of formulas. The recursive formula is a direct translation to what I see in words, where I have the first term equal to 1, and in general, I can get a term by taking the previous one and adding 3 in this case, and that's going to apply for positions 2, 3, 4, and on. And then on the other side, I have the explicit formula because the recursive formula translation-wise is nice, but it's not that useful to handle a variety of problems in terms of counting how many terms I get to a target and all kinds of things like that. So we looked at another way of figuring out a pattern, excuse me, and we saw it's the first term plus n minus 1 times the constant difference, and that will allow me to get any term that I may want. Now we've sort of seen it here and there in our initial discussion, but there are sequences that are built on top of this arithmetic pattern where I add and subtract something from one term to the next. If I look, for example, we can just look at our exercise, honestly. Drag it over to show you here. Exercise 2.5, number 1. That should be fine. Let's just move up a little. Exercise 2.5, number 1. Sequence is 5, 6, 14, 29, 51, 80, and so on. So now what I can do based on my experience is certainly say, okay, well, let's look at the number that is added every time. I'm just going to do it a little bit differently. I'm going to do it like this. The number that I add is 1, of course. Then I'm adding 8. Then I'm adding from 14 to get to 29 is 15. And then I'm adding 22. And then I'm adding 29. So let me make this extremely clear. This is not, let's say, the original is not an arithmetic sequence. For it to be classified as an arithmetic sequence, I have to have the same jump every time, add or subtract the same number every time, and clearly this doesn't happen. However, we're not completely lost here, because when we look at what I'm adding and see that as a sequence, then I can see, well, I'm adding 7, and I'm adding 7, and I'm adding 7, and I'm adding 7. So there is an arithmetic sequence deeper down once I start looking. But the original is not an arithmetic sequence. So here is the sequence. Let's say original. When we look at how much I add every time, one level down, we call that the first difference sequence. It's a sequence in its own. It has the numbers 1, 8, 15, 22, 29, and so on. I can go a level further down if I want to, and in some cases I might have to, and the further I go, I just count the levels down and so on. But in this case, this first difference sequence, this is an arithmetic sequence. So my original sequence is built on top of an arithmetic sequence. Itself, it is not an arithmetic sequence, but it's built on one. It is connected to an arithmetic sequence. We'll call the original sequence, that was supposed to be a C, we'll call it not an, just a generalized arithmetic sequence. It's part of a bigger family. There is the very specific and convenient arithmetic sequence in general, like this top one, like this one. But if I sort of zoom out, this is a special case of a larger collection of sequences, all somehow related to adding the same number every time. But this larger collection of sequences has, each one has that property, but maybe further down in the levels. So it's a little more general. It's based on an arithmetic sequence, but deeper down. It's a little general. So now I admittedly ran out of space here because that question asks me, I believe, to find the next two terms. I might, yeah, I'm going to need some space here. Or bigger, that would help. Yeah, erase. Now, the fact is that just like a recursive formula is super easy to work with, relatively speaking, if I just want to find the next two terms in the original sequence, that's also quite straightforward. I just have to go down into these difference levels until I see an obvious pattern. What's more obvious than all the numbers being the same? So now if I go down to the second level, I can say, well, okay, let me just make some lines here so my positioning is good. Something there, something there. But if I go further down, I know that 29 plus 7 is going to give me this next one. So I know that's 36. And 36 plus 7 is going to give me this one. So I know that is 43. And then I can go up to the original sequence and say, well, from 80, I need to add 36. So that's 116. From 116, I now know that I have to add 43. So that's 159. So if I just go deep enough until I see everything pretty much being the same, the level before that is an arithmetic sequence, and I can sort of reverse the process to find the next missing terms in the original sequence. So we call these, I said, these are, the method that we're using here is just using differences. Now, I don't know which level it's going to be until I see a nice pattern. But you see here it says, use differences to find the next term in the sequence. So yeah, you can read in the book here if you want to. I've sort of made it a little bit more official. The difference is just the like the word suggests, the difference between two consecutive terms. And I can get more general sequences based on this arithmetic concept. Let's do number 2. But I don't know by looking at it how far down I would have to go to see the obvious pattern. I definitely don't want to stop early and guess. If I go far enough down with a general arithmetic sequence, eventually the differences will all be the same. And if that never happens, well then it wasn't a part of this type of sequence. 2, 3, 9, 23, 48, 87. Of course, not everything will be like this, but it's a good next step to expand my experience. So then the question also makes it pretty easy. It says use differences. So I'll use differences then, since you insist. So first level, first difference is 1, and then a 6, and then a 14, and then maybe it's something you can still do in your head with confidence. Maybe you need a calculator. I'm not going to judge. Ideally, I'd want to, even if I slow down, practice doing at least 2-digit arithmetic to just keep myself sharp. Uh, the temptation of a calculator in my brain just turns to mush eventually, right? So even if it slows me down, like it does perhaps here, ooh, I have to think, 25. And then what would this one be? 30 would get me to 78, and then another 9, 39. Verify it on your calculator, but it's a really good idea to just practice, slow down, and just take your time and just brain cells working. It's always easy to make a mistake, but at least I tried. That trying makes a big difference. So now let's see. I don't see a pattern. Maybe. Well, they're not the same. I want to be sure. So I look at the next level, 5, and then it's an 8, and then 14 to 25 is an 11, and then 25 to 39 is a 14. Now, I have some experience, and this does look a little familiar, but I can go further down and verify that that is an arithmetic sequence over here. Arithmetic. Because the differences for that is all the same. The original is not arithmetic, but somehow, somewhere deep down, it's built on an arithmetic sequence. Now I just have to find, am I looking for the next 2 or just the next 1? Oh, just the next 1. Oh, that fancy then. Just looking for 1. But be aware, maybe it might ask for 2. But again, I can only really use this one step forward and then another step and so on. I can't jump. So it's in the realm of recursive thinking that I have to do them one at a time, unfortunately. But it's a good first step, just like we started with recursive formulas. Let's do this. I need to find that one, right? First difference. In order to do that, I need to find this one. Then in order to do that, I need to find this one, but I know that's a 3. So this will be 17, because this second difference sequence level is arithmetic. Then the first differences are built on that. 39 plus 17, well, that's 49. That's 56. And then lastly, I can go to my original sequence, which needs me to add 56 to this to find the term that I'm looking for next in the sequence. 87 plus 56, I stop. I force myself to try and do this in my head. Yes, I can be faster with a calculator, but in the long run, I'm just losing. It's just a losing game. But I can verify my answer afterwards. We can do that, sure. 87 plus 56, well, 87 plus 50 is 137. 137 plus 6, 143. Just so we see something in the chat. Why not? See if MathBot is awake. Let's show that same calculation. Let's suppose you're not super confident. Take the time, practice it, but then double check. That's okay. Then you get the best of both. You're right, and your brain is still working. So 87 plus 56. We're not going to be even remotely proficient with arithmetic calculations if we don't pause and make a point to practice it. But no one says you have to be super fast. 2-digit addition, dip some toes into 3-digit, they're fine. Okay, so the concept of differences, I hope, is not too overwhelming or strange. I can get these sequences that are built on an arithmetic sequence. I don't know how deep down, but they're there somewhere. And they're called generalized arithmetic sequences. In truth, I'll be perfectly honest with you, I don't know what they're called. I don't know if they have a general name. So I just named them something appropriate. I don't think they really have a name. In certain cases, certain types of them have names, but I don't know if the family in general has a name. So I called them generalized arithmetic sequences because that is what they are. Let's look at a specific group of those where I can, and this is the end of this chapter, I can use simple geometric shapes to make sequences. Let me show you. I'm going to make a sequence, but instead of the numbers, I'm going to make a picture. There's my picture, one dot. So easy, right? One dot. Next, I'm going to take that one dot and put 2 dots underneath it. Next, I'm going to take those dots and then put 3 dots underneath them. I'm going to copy that. Time making dots and put 4. I moved them way too high. Let me backtrack. That's way too high. Too high. Copy. And then put 4 dots underneath. And you see the shape I'm making is a triangle. Copy. 2, 3. That is what was there before. And put 5 dots underneath. And I continue like that. And then the sequence that I get is 1, 3, 6. What do I have here? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have the existing 10 with another 5, so 15, and continue. We'll call these triangular numbers, or just triangle numbers. Sure which one's preferred. Use either one. Triangle numbers. Now, is this a generalized arithmetic sequence? Well, I'm going to erase this in a second, but if you want to verify, the first difference is a 2, then it's a 3, then it's a 4, and you see the sequence of differences, first differences, that is an arithmetic sequence. So this is a generalized arithmetic sequence. Now, the reason why these sequences in general don't really have one name is because the formulas don't really extend to all of them in exactly the same way. It really depends on how deep down the differences sit. If the difference is at one level down, if the arithmetic sequence is one level down on the first differences, then it's a much easier game than if the arithmetic sequence sat deeper down. So That's why they're handled differently depending on where that arithmetic sequence sits. But just to give us a taste, we're going to look at the triangular numbers, which has arithmetic sequence at the very next level, the first differences. So now I could come up with a recursive formula, but the differences are sort of doing that already. It's already recursive thinking, and whether I explain it in words or the mathematical language, it's not very helpful. But let's see, we can certainly try, even though it's not gonna be super helpful if you want to do stuff in the future with this. The recursive formula is a nice translation practice, which is just rephrasing what we say in words here. So I need to know where to start, like I always do for the recursive formula. Now I need to say it in words first, right? I don't know. I don't memorize these things. I'm adding 2, then I'm adding 3, then I'm adding 4, then I'm adding 5, and so on. So let me rephrase that, say it again. Let's look at the positions to help me. Position 1, position 2, position 3, position 4, position 5. It's a good exercise to make recursive formulas because it's such a direct translation exercise. Okay, so let me rephrase this. To get to position 2, I added 2. To get to position 3, I added 3. To get to position 4, I added 4. Do you notice a pattern? What I'm adding is exactly the position I'm going to. So if I want to find position n, I take the previous one and add n. Now that's not going to be the same for any generalized arithmetic sequence. It's specific to this one, which is why they don't have a name. Every one's going to be a little different. So because it's not an arithmetic sequence, fancier, because the number I add changes, I can link that change to the position I'm trying to find, and in this case it's the easiest in the sense that it's just the position value itself that I add, showing that the further into the sequence I go, the bigger my jump is going to be. Now, of course, we don't want to run with this too far and make it too complicated. Just triangle numbers and then some little extra idea afterwards. Not very helpful because I still have the recursive downside of finding the next one, finding the next one, finding the next one. Not too useful. So let's see, can we in this more complicated case at least see what makes things more complicated? And in searching for an explicit formula, I get a taste for, ooh, this is already a big step up. So I can sort of see into the future how complicated things can get. There's really no end. Now for me, remember now, in my explicit formula, I'm looking for some calculation involving just the position. No idea what that is. What helps me is a table where I relate the position to the term in that position. Now positions 1, 2, 3, 4, and 5 should be sufficient. Extend my line here. First term was a 1, then a 3, then a 6, then a 10, then a 15. It still helps me to lay this out when I've never seen this before. Yeah, that's pretty much the reason. When I need to sort of do something from scratch, I've never seen it before, there's no formula I have memorized or anything like that. Well, this is an option. Okay. Lots of time. Let's see what we got here. So, like I almost always just skip the first one. The first one's a special case. I do need to come back and check that it works if in whatever pattern I see, but that's not where I start. You can even start in the third one, but second one should be fine in this case. So how do I get this 3? We said it was 1 plus 2, the 1 being from the starting point. Then to get 6, it was the previous 3 plus 3. But that 3 itself has an expansion of 1 plus 2, and then this 3. To pull apart 10, just one step, it was 6 plus 4. That's 6. But this 6 in itself has expansion 1 plus 2 plus 3. 1 plus 2 plus 3, and then the 4. Whoops. Is extra. 15 is 10 plus 5, this 10. But the 10 is 1 plus 2 plus 3 plus 4. And then I add the 5. Okay. So now if I continue this pattern, which hopefully you all can see, what is now the link between the calculation of the term and the position? I always start at 1. I always add consecutive numbers, 1, 2, 3, 4, 5, 6, 7, 8, however far I go depends on the position. This one, I stop at 2, the position is 2. I stop at 3 when the position is 3. I stop at 4 when the position is 4. When the position is n, I'm going to stop at whatever the value of n is. So the value, this is 1. This is the calculated, let's say, value of term an in position n. That answer is the term. The calculation is longer depending on how far I go. Now, these dots just mean the pattern in the addition calculation continues, but that's not good enough. That doesn't help me, because what if I look at this sequence above here and I want to find the term sitting in position 100? Still not that useful. So for example, I'll write it out. The term, that's supposed to be an M, term in position 100 is a 100, and it's calculated as 1 plus 2 plus 3 plus all the way to 100. That's not easy to do, so it's not a useful formula yet. It's not quite in the right form. So now I need to figure out, well, what is the compact version of this? Now, of course, some of you may remember 142, where we did do this, just sort of as a side topic. But it was also very early in 142, which means it's months ago, might not remember. And it's also not a requirement that you do. So now we have to figure out this. And by doing that, we'll see what the explicit formula of the original sequence should look like. So I'm going to give myself a little bit more space and look at this specific example first. What I'm going to do is write this same sequence of what I need to add in reverse. So it's going to start at 100, and then 99, and then 98, and so on, and of course end in 1. Now, I'm ultimately trying to count this. Let's call it S for sum. The sum of these numbers is what I am looking for. Writing them in reverse is the same collection of numbers that I'm adding. So that's also S. So now I'm going to add all of these together. What I would get on the left is double the S value, because I have an S there and I have another S there. That's two S's. So I have to merge all these numbers together, but I'm going to do it in a specific way because I don't want to actually manually add them all. I'm going to add just those two together and I'll get 101. Then just those two. As long as I merge them all eventually, I can do it in whatever way I want. Merge those two. And every time I get 101. Now I still need to merge the 101s. However, they're all the same. So that's repeated addition, which is multiplication. I just need to figure out how many there are. And there are, well, the first one, second one, third one, there are 100 of them, of these 101s. So the answer to this right-hand side is 100 times 101. Repeated addition is multiplication. That means 2 times the value of S, which is what I'm ultimately looking for, is 100 times 101. So S, S equals 100 times 101 over 2. Now, I don't want to calculate this because this is a specific example and not actually what I'm trying to do. It helps to look at a specific example, but my ultimate goal is to figure out what is this, where I don't know the end number. I took 100 as an example, but that's going to rarely be the case. I need to be flexible to handle any end position. This one is 100 times 101 over 2. But what if I have a different end number in mind? So I need to generalize this. Luckily, that's not that big a deal. I just need to leave it open and say, I don't know where I'm going to go. I'm going to stop at n. My strategy is the same, but I don't know what they are when I write them backwards. So that has to be dependent on the choice of n. This will be n. This will be 1 less. This will be 2 less. Now what I'm getting when I add the pairs in the same way as before, taking the time to erase all of these with a very, very small cursor, I get n plus 1. This is also n plus 1. This is also n plus 1. This is also n plus 1, which I kind of need. I need this to be repeated addition. And there aren't 100 of these n plus 1s. There are n of them. So the argument's exactly the same. Repeated addition, n times n plus 1. And at the bottom here, we can do so much erasing, so much erasing, so much erasing. I could make my cursor bigger, but that would ruin the fun of all this erasing. I have n times n plus 1, and therefore dividing by 2, n times n plus 1 is the answer. This is n times n plus 1 over 2. Now what was this? This was the value of the term an in position n, which is exactly what the explicit formula, what the goal was, to find the explicit formula. So the explicit formula is that same thing. So the explicit formula of the triangle numbers is n times n plus 1 over 2. And any generalized arithmetic sequence that has first difference, an arithmetic sequence, can be done this way. I picked a very easy one. If the jumps are bigger and they start at a different point, then of course it's a little bit more complicated. You're not expected to know anything past the triangle numbers and its formulas. That's one, just seeing. This does get a little bit more complicated with just one step, just building on top of an arithmetic sequence. Imagine if that arithmetic sequence sits further down, like this one sits uh, another level down. Then it's much more complicated, which will take too long for us to explore here, and it's not really the point. Okay, so that's one thing. Then the last thing is, let's look at these triangle numbers, and that gives me an idea. I can make little triangles. Can I make other shapes? I can make little squares. What about little pentagons? Now, we're not going to go too far, but yeah, we have these sort of polygon number sequences. Now, they're not necessarily generalized arithmetic sequences. We're now going off in a different direction, looking at the shapes and what sequences they can create. So, because my drawing skills are quite limited, on Wikipedia, I just did a search with their diagrams being nice and clean. So, we can make a variety of shapes and then systematically increase those. The triangle numbers or triangular numbers we've seen. Now they added them on the side there, but it really doesn't matter because of the triangle. We can also start with a dot and make a square, and then extend the square, and then extend the square, and then extend the square, and we get the numbers we've seen before, the square numbers. Now, I'm not saying they are necessarily generalized arithmetic sequences in the exact same way, though. What do we add here? We add 5, then no, we add 3, 5, 7. It isn't a generalized arithmetic sequence, but the formulas won't look exactly the same. Everyone's going to be a little different depending on what that underlying arithmetic sequence looks like. So don't worry about that. This is now off to a different direction, looking at the pretty shapes. Then I can go further and say, oh, what about pentagon numbers or pentagonal numbers to be fancier? Start with 1, make a little pentagon. Then the gray one is my previous pentagon, and extend around it, and extend around it, and extend around it. And I get these numbers. I can make hexagons. Start with a dot. We always start with 1 dot. Make a hexagon around it, extend it, sort of attached to it. Just extend around it, and you get the hexagonal numbers. Now we'll stop there, but of course there's no end to this, right? You can keep going and explore those things. And just for interest's sake, they do have a formula here. We don't need to care about the formula, but you see things are getting a little complicated. Oh, no, let's scroll it back up. We don't want to see that. It'll freak me out. So what do you have to be able to do? You just have to be able to find the first 5 triangular numbers, square numbers, pentagonal numbers, hexagonal numbers. Now you could memorize them, but you have to be able to draw them as well. Because it's open book, right? So copying numbers that you could look up wherever, your notes or Wikipedia, that doesn't show any insight. But maybe even copying this diagram is not the simplest thing in the world necessarily. You need to pay attention to how we are extending these larger shape numbers. Today we're ending a little earlier. That is the end. I am not going to go into the next chapter, which is on a different kind of sequence. And soon we are at the end of part 1. Very exciting times. Are there any questions at this time?
Are there any problems that you would suggest doing first?
Ooh, that's a good question. Let's see. Let's go to the problems. I'm always going to forget that. So yeah, that's going to be a recurring question, which is good. So the pure arithmetic sequence problems are 2.1, 2.2, 2.3. Let me just check. Is this on the screen correctly? Yeah. Those are the straightforward arithmetic well, not straightforward, but just an arithmetic sequence using the arithmetic sequence explicit formula, probably. Actually, no, problem one says state both. Okay. Problem 2.2, it's an arithmetic sequence. Problem 2.3, they tell me it's an arithmetic sequence. So these mirror the exercises that we did very closely. Then problem 2.4, you can tell it's going to say use differences. And it's exactly like that exercise. What was it, 2.5? What did I do? Oh, right. Exactly like that. You just have to dig down and see how far do I need to go before I spot that arithmetic sequence, and then one level below that will all be the same. Here I just have an interesting little spin on that same idea as 2.4. And then in problem 2.6, I just get you to practice drawing those two. We're not going to go past hexagons. It gets a little tedious. So yeah, since we're done with the chapter, all the problems are good. All the problems are important. I can't leave anything out. But I would do them in order. Yeah, I would do them in order in this case. That's not always the case, but in this case, it'll definitely work. Any other thoughts at this time? It's been very quiet. Is it because it's too easy? I'm sorry. I don't want to make it more difficult than this. We don't need to be more difficult than this. So I apologize if I'm boring you. It's good enough for us. It's good enough for us. And remember, we have, oops, bumped into my mic. We have many a session where you can ask questions and talk about things. My recommendation would just be
Is the an equals n times n plus 1 over 2 the only thing we need to know for the generalized arithmetic sequences, like the only explicit formula we need to memorize? Okay. Okay. We don't need to know we don't need to know the formulas for all those ones, just how to draw them. Okay. Okay, perfect. Thank you.